Welcome back. Good afternoon. I hope you got everything that you wanted to get done. Or if you're like me, you're wondering, where did the time go? How has a whole week passed? Didn't get nearly as much done as I hoped to. That's always the case. I know that going into reading break, but I always hope. So that's okay. So it goes. Let's get in closer here. All right. So you guys got all set up with GitHub. There wasn't much to the assignment itself, right? Basically, open a pull request, and then that was it. And then I'll be able to see that you did that, and that's it. But the goal is for you to work through, because we're all starting at different levels of comfort with Git or GitHub. And if you prefer to just use straight up Git, then that's fine. But it's just a little bit easier to see if you're using GitHub. Okay, so so the goal is for you to see all the things that you might not know, and then to slowly start picking away through those tutorials and slowly just trying to learn about version control and GitHub specifically, and then so that's how we're going to learn, and that's how you would tackle anything. You're introduced to a problem, and then you slowly pick away at it, and that's how we learn, right? So so nice work. I was tempted to overload you, and I decided not to over reading break. So you really only had the GitHub assignment, I think, and those multiple choice questions from chapter 1. And I held off on purpose until after reading break, but I'll post the chapter 2 questions. But from looking at the multiple choice grades, those are really high, and that's what I want. Okay, and so keep practicing those. They'll come up on the test. And speaking of test 1, I've been saying, oh, we'll do it after chapter 3. And today we're starting chapter 3. So it's time to nail a date down for test 1. Now, I am looking for your feedback, because I want to do it on Tuesday next week. Okay, but I don't know what your other classes are looking like, or if Thursday would be better, or if you would prefer to just have it a timed quiz that's available for some amount of time, right? Maybe in a specific day, we can do that as well. And then you could use the class time. So kind of, I know I didn't really give a yes or no question. That's bad of me. But test 1 is going to be next week. But what I'm looking for is kind of feedback on when you would prefer to have it, given your other due dates and stuff like that. Okay. And so we will start chapter 3 today, and finish it this week. Mostly because it's pretty well reviewed, but with a data science twist, okay, on hypothesis testing in particular. And so that's why we'll be able to move quite quickly through chapter 3. And I'm just going to kind of introduce the spots where it would be different in data science versus what we did in Stat 230. So that's what we'll do. We'll start today. And so we'll start chapter 3 today and finish it this week. And then we will have test number 1 next week. So I have a couple of different options. Option number 1 is Tuesday next week, or option number 2 is Thursday next week. Oh, here come the dates. March 8th is the Tuesday, yeah. Or March 10th. Just because there's a cat after. We've got 1 vote for option, oh, sorry, I said number 3, but it's actually number 2, you're right. Or option number 3 is just to have it open. Option number 3 is a timed quiz open open over some amount of time. And so what I would do probably is what I'm leaning towards is maybe having it open over the Thursday class. So we wouldn't meet on the Thursday, but you could sit down and do the quiz and use that scheduled time if you wanted to. So open from, let's say, I don't know, 8 to midnight on March 10th. So you could use our scheduled class time. It sounds like option 3 is the preferred option. So you could use our scheduled class time, but don't have to. But that means that I'm saying it like it's a bad thing, but that means that we won't meet on March 10th. Maybe you guys are okay with that. No meeting on March 10th. It feels like we have a lot of votes for option 3. Perfect. Yeah, I like the flexibility that it gives you. And so I think we'll go for option 3. Which means we did not go for those. It's like the only one that got any votes. Well, besides option 2, when there only were 2 options. Now it's option 3. Okay. Okay. So this is the one that will, and I like the flexibility. I can even have it open earlier if there's time zone issues. So maybe that's what we'll do. I can do that. (0:00). How about 12:01? Just to be gets confusing. I'm just going to keep it as 8. But I can actually make it open whenever. And so we can do whatever we want. Okay, so one kind of heads up is that we're likely going to cover material that's not on the test on the Tuesday then. Okay, so the reason I wanted to do it on Tuesday initially is because that way we don't cover new material that's not on the test, right? And so, but as long as you're okay with that, so then our schedule is going to be, today we're going to start chapter 3. And on Thursday, we're going to finish chapter 3. And then I'm not counting the labs. Tuesday, which was March 8th. Start chapter 4. And then Thursday, which was March 10th, we said, we'll have test number 1, which is on chapters 1 to 3, right? Not chapter 4 from the previous day, okay? So that's the only confusing thing, potentially, but besides that, hopefully you're okay with that. And it gives you more time to review and work through some problems. Okay. So my plan, and it might be too easy of a test, I'm not sure, we'll see. I'm willing to test it out and see what happens. I'm okay with everyone having high grades as long as you deserve them. So then it doesn't matter to me. But what I want to do is take those the multiple choice questions and basically smush them together for all the chapters, and then that'll be your test. Okay, so a timed, just open book, no working with each other situation. Okay. So good. Hopefully that makes sense. And I'll just highlight here that on March 10th, there's no meeting because you could do test 1 if you wanted to. Okay. One problem with having it open is potentially that you can't ask me any questions, but especially with a multiple choice question, they're pretty straightforward. So, so that's why I feel comfortable doing it this way. And I'll try to be on high alert if I get a message or an email. Okay. So let's see here. Chapter 3 is on statistical experiments and significance testing. So statistical experiments and significance testing. Significance testing is hypothesis testing, right? We typically have called it, hypothesis testing. Yeah. So in Stat 230, right, we called it hypothesis testing, but we're really, we're going to start calling it significance testing. Why? Because hypothesis tests allow us to say that there's a statistically significant difference. Okay, and so so then it's kind of more mature to call it significance testing, but I call it hypothesis testing in Stat 230 just to emphasize that, okay, you have to set up your hypotheses and you have to work through a set number of steps to do it properly. Okay. So in Stat 230, we talked about we introduced this classical statistical framework for hypothesis testing or for significance testing. And so in Stat 230, we introduced the classical statistical inference or significance testing framework. We introduced the classical statistical inference or significance testing framework. Usually it relies on some sampling distribution. So for example, we know that if I'm comparing two means, right? So I have two groups and I'm looking at a numerical variable. So I'm comparing the means typically. Then I would use the t distribution because I know from just kind of prior knowledge and tons of research has been done, we can assume that it follows a normal distribution and a t distribution to be specific. Okay, and so then I know that I would calculate a t for my test statistic. And then I know how to find p-values for that test statistic, etc. Okay, and so if I'm comparing many means, right, more than two means, I would use an ANOVA, which gives me an F statistic. And so we have this knowledge of, okay, well, I can model that behavior using this sampling distribution. So now what we're going to move towards is we're not going to rely so much on that prior knowledge and say, okay, well, if I'm comparing two means, then I know that it's going to follow a t distribution with some degrees of freedom, right? And so we're not going to rely on that so much because we have computers now. Okay, and so nothing changes really. It's just how we arrive at the conclusions is going to be a little bit different. Okay, but the idea stays the same. So in Stat 230, we introduced the classical statistical inference or significance testing framework. Okay. This framework typically relies on knowledge about the sampling distribution. Knowledge about the sampling distribution. And there are many cases where we're still going to go back to that. Okay, and so that's what we saw in chapter 2 was we talked about some different distributions that we could be pulling from. And so, for example, if I have a success failure, so only two possible outcomes and a couple of other conditions, but that's from last chapter, so we won't go into it, then I can model it using a binomial, right? And so, so same idea here, right? We have this knowledge and it'll still work, right? But now we kind of want to get away from that, especially the conditions that we had to check before. Okay, and so this framework typically relies on knowledge about the sampling distribution as well as checking conditions, often about normality, often concerning normality, right? Can I use a normal distribution or no? Can I assume that I have a normal distribution? Okay. So now in data science, we kind of move away from that a little bit and we introduce this idea of resampling. Now I don't want to use the wrong word, and I wrote it down somewhere here, but now I can't remember. So anyways, that's okay. We've seen the bootstrap, right? Where we have a sample, and even if it's, not a huge sample, we can still collect new samples from that sample, right? And I can, with replacement, I can collect a brand new sample and I can replicate it. And so now it's a similar idea, but now we do it without replacement, and that's basically the only change. So, but I got ahead of myself, and let's take it back a little bit. And so we've seen some different hypothesis testing types of questions, right? And so one of the main ones that we're going to be concerned with is what we call A/B testing. Okay? And so we have seen many different types of hypothesis testing questions. So we have seen many different types of hypothesis testing questions. One sample mean, paired samples, two independent samples, one sample proportion, two sample proportions, multiple proportions, multiple means, right? And so the list goes on. And we've seen all of those. And so things like one sample mean, paired samples, two independent samples means, two independent sample means, multiple means, or on the proportion side. So if it's a mean question, then you can have one sample mean, paired samples, two independent sample means, multiple means. Or if you have a proportion question, then you have one sample proportion, two sample proportions, multiple proportions, which we test using chi-squared, right? So here we know how to analyze these in the classical sense, and it's absolutely safe to just go ahead and use those methods that we've already established, right? But what we're going to do is we're going to flip-flop back and forth, and so we're going to introduce this kind of new way of analyzing a difference between two means or two proportions. We're going to focus on two. And then we're going to look at kind of comparing it to the classical way, and what we'll see is that they're very, very similar. Okay, but one doesn't rely on all these assumptions that we have to check. Okay, and so the two independent sample means or the two sample proportions, these are what we call A/B tests, right? Two different outcomes that we want to compare, right? Which means comparing two groups. Notice that it can be for numerical data. So if we're comparing two means typically, or we compare two proportions to each other, either way, we're comparing two groups, and that's where the A/B testing comes from, that terminology. So we've already seen it. We never called it A/B testing, but it's really just comparing two groups. So A/B testing is an experiment comparing two groups. Okay. So one thing that we're going to really focus on is, okay, I have some new and improved way, well, maybe not improved, but I have some new way of doing things, right? For example, maybe I updated my website. Am I getting more sales? Are people spending longer on my web page, right? Just kind of focusing on web analytics, because that's kind of at the forefront of data science, right? Is kind of this web analytics realm. And so who's clicking on my website? How do I do that? How do I get sales? That kind of thing. And so usually I have some standard treatment that's already being employed. So for example, that would be the old website, and then I introduce this new website. So in order to determine if this new website should be used or not, then I would typically compare two metrics, right? And so I have to decide in advance what those metrics are. Am I going to compare the mean sales from each of the websites, or am I going to look at the proportion of clicks, right? Am I going to look for something else, right? And so I have to decide that in advance of my experiment, so that I can design my experiment properly. Okay, and so the two groups are typically the control group, which is the standard or the existing treatment, right? And so usually it's the thing that we're trying to replace or threatening to replace. So the control group is the standard or existing treatment. Okay. So I have a control group, and then I have a treatment group, as opposed to the existing treatment, right? I'm comparing two groups, A/B testing. And so the treatment group is going to be kind of the new treatment. They're the ones who get the new treatment. So the treatment group, this is the new treatment, or kind of the one that we want to compare to. Okay. The reason we need a control group is pretty straightforward, right? I think intuitively we understand that, okay, I can't just look at two new websites and compare the two if I don't know how they have changed in some metric from what I used to be doing, right? And so that's pretty basic stuff. And I think intuitively we have a pretty good handle on why we need a control group, right? And so you don't make changes unless you've compared your new treatment group, so your kind of new treatment, to the old control group. And so because you're trying to minimize all things that can influence your sales, for example, right? So let's say, for example, right, if you have a control, if you don't include a control group, right, then your treatment group might see an increase in sales, but it could be due to a number of factors, right? Not necessarily just the new website that you've put out there. Maybe it's because you know, it was payday, or I don't know. I don't think we all have the same payday, but actually, I don't know. No, I don't think so. But I don't know. Right. Or maybe there's just been COVID lockdowns, and that's changed the sales, right? Your online sales have increased because of that. So it's not necessarily because of your new website, it's due to something else. So to try to eliminate that, or the outside factors, right? That's why we have the control group. Okay. So subjects are randomized, or should be randomized at least, but let's assume that they are, right? So subjects are randomized between the two groups, right? And so subjects are randomized so that any difference between the groups, right, is due to two things. So subjects are randomized so that any difference between the groups is due to the effect of the different treatments, and that's what we're hoping to kind of pinpoint. Okay, so the effect of the different treatments or potentially just the luck of the draw. Now, this is what we're trying to avoid, right? And so maybe you just have, even if you've randomly selected people to participate in your different groups, right? Maybe you've just, luck of the draw has assigned the spenders to the treatment group and the non-spenders to the control group. That can happen, but we randomize to avoid that, right? And so, but that is an option, right? So it's either the effect of the different treatments or just the luck of the draw or the unluck of the draw, I guess, because the luck of the draw, which we usually call just random variability, right? But we randomize to try to minimize the probability of that happening, right? I don't say the word probability lightly because we use that term a lot, right? But in this case, it's true. So, okay. So subjects are randomized so that any difference that we see is due to hopefully the effect of the different treatments, or potentially we always have to remember that maybe just a certain group was assigned to the treatment group, right? So what this is saying is there is a possibility that people who spend more were randomly assigned to the treatment group. That people, oops. Oh, that people who spend more were randomly assigned to the treatment group, or vice versa. Doesn't really make sense to say vice versa with only one option, but I think we understand what I mean there, right? That they were randomly assigned to either the treatment group, and maybe I should clarify, or the control group is what I meant by saying. So selection bias is when we tend to favor certain people into our sample. So here the difference, and it's very, very subtle, right? The selection bias doesn't really apply if we have randomly, oh, I don't know the World War II fighter plane example, but sounds reasonable. So as long as we're randomly assigning people, then we're trying to eliminate that selection bias. So although it kind of has the same face, right? You have this bias, right? Those people who spend more have been assigned to the treatment group, but there's also that probability of, okay, well, or I should say possibility of, even if they were randomly assigned, right? Some of those random assignments are going to lump the spenders into one group and the non-spenders into another group. But it's very unlikely, but that's the difference. Okay, so so as long as we randomly assign it to a group, then we can say, okay, it's possible that that happened, but it's very unlikely, right? And so in that case, the effect of the different treatments is probably the reason that I see a difference between the groups. Okay. And maybe I'll underline, so there's a possibility. Nice. Okay. So before we do an experiment or conduct an experiment, what we need to do things properly, and this is not always the case, this is not how we do things in reality, but if we were to do things properly, what we should do is we should decide on the metric. So am I looking at the mean amount spent, or the mean amount of time spent, or the proportion of clicks or something like that, right? So I should decide on a metric before I conduct my experiment. But not only that, in deciding my metric, I should also decide what my hypothesis is, or my hypotheses are, right? And so before conducting an experiment, so before conducting an experiment / collecting data, right, / collecting data, we should, and I'm going to underline should because it's not always the case, but I'm here to tell you, okay, the things that we should be doing to do things properly. Well, what we should do is we should decide on a metric beforehand. Decide on a metric. So number of clicks, or maybe I should say proportion of clicks. Average sales. Etc. Okay, so some metric that you're interested in, and this doesn't really read like metric, and it's kind of an important word. So there. Okay, so decide on a metric, and if you've decided on a metric, right, maybe it's the difference in sales or something like that, then you've also decided your hypothesis. So you may as well establish that beforehand, and you should, right? So, and the second thing is to establish the hypotheses you will be testing and this, of course, depends on the metric. Okay. So you should decide on the metric that you're going to investigate first before you go ahead and collect any data. And so that's kind of opposite to what we usually do, right? I give you a data set and then I might ask you, hey, is there anything interesting going on in there? Or I might tell you, consider this and look at this metric, right? So then I've told you what the metric is. But if we're doing things start to finish, then we should decide on the metric that we're interested in, then collect the data, and then analyze it. And I guess establish the hypotheses before we collect the data. Okay. That's what we should do. Not always the case, but what we should be doing. Okay. So the hypotheses you should remember, you will remember, we have a null hypothesis and an alternative hypothesis. Okay. And so our hypotheses, we have our null hypothesis, which we denote by H naught. And that's going to be our baseline assumption, right? The treatment group is the same as the control group. Just the baseline assumption in general. Okay. And the one that we're interested in knowing if it's reasonable or not, the alternative hypothesis, I use HA, but you can use a capital A, a lowercase a, or even a 1 to kind of match up with the H0, H1. But the alternative hypothesis is what we hope to show, right? And so what we hope to show, right? We hope to show that the treatment yields significantly higher sales than the control group, right? My new website that I've put out there yields significantly higher sales than my original website, right? That kind of thing. And so that's what I hope to show, but I can only do that by first assuming that they're the same, right? And so we still do all our testing assuming the null hypothesis is true. So we do all significance testing. Assuming H naught is true. So that's the same. And so we go ahead and we assume that the baseline assumption is true until I'm able to say, okay, well, if that's true, then what I saw is really extreme, right? So it's very unlikely to happen. Now, it's possible that I just had a weird random assignment of people into each group, or observations into each group. But more likely is that it's due to the effect of the treatment. Okay? And so that's the key behind hypothesis or significance testing, is this idea of, okay, I assume the null hypothesis is true until I have enough evidence against it, then I can say, okay, well, then I reject H naught. And I am able to conclude that the alternative hypothesis is reasonable. Okay. And so just a review on the hypotheses, and also to add something, because in Stat 230, at least if you were in my group, I like to only have equal signs in my null hypothesis. And so we talked about one-sided tests in the alternative, which means I have less than or greater than, right? Then I'm only concerned with one side. And what we said was, okay, well, our default is a two-sided test. Okay, and so that covers all my bases. It's either equal to, let's say two groups are equal to each other, or they're not equal to each other, right? When I introduce a one-sided test, or a one-way test, we could call it, and that's what this textbook does, then I would absorb the opposite in my null hypothesis, okay? And so, for example, for our hypotheses, let me see how I can write this out here. So just a little bit of review on hypotheses. If my null hypothesis is that mu1 equals mu2, okay, then my alternative hypothesis would be that mu1 is not equal to mu2. Okay. And so I have to assume that these two means, and let's say we're talking about sales, right? Then I would have to assume that they're the same until I have proof that they are not the same, right? And that's what I'm hoping to show. Okay. Versus a null hypothesis where mu1 is less than or equal to mu2. So now this is kind of new for us, but it's not that crazy. Less than or equal to mu2. Well, what's the alternative? Then the alternative hypothesis is going to be that mu1 is greater than mu2. So notice how we always include all the possible options, right? So our hypotheses have to span all possible options. The other option, the last option, is that mu1 is greater than or equal to mu2, which means my alternative hypothesis is that mu1 is less than mu2. So H0 and HA must incorporate all options, must incorporate all options. Whereas before, right, I tend to simplify things and just say, okay, my null hypothesis is always that mu1 is equal to mu2. Okay, even if HA is that mu1 is greater than mu2 or mu1 is less than mu2. So then I kind of ignore the other option, but nothing really changes, right? Because if you have enough evidence to reject H0, then you can conclude that mu1 is greater than mu2, which means it's not less than or equal to. So that includes the equal to, so it doesn't really matter. So for me, it simplifies things if we just have an equal sign here, but for now, now we're going to grow a little bit, and we're going to start to incorporate all the different outcomes. Okay. So when we're concerned with only one side, so one extreme, right, then I'm going to call that a one-way test. Now, usually I've been calling it a one-sided test or a one-tailed test, and so now a one-way test or a two-way test, that's the same thing. So this is a two-way test, and these are one-way tests. right? And it depends on the sign in the alternative hypothesis. One thing that you might remember is sorry, I noticed it's all fuzzy, but anyways, weird. Hello there. Okay, so one thing that you might remember is that the sign in the alternative hypothesis, that's how we decide how we calculate the p-value, right? So recall that the sign in the alternative hypothesis, which I'm just going to abbreviate HA, determines how we calculate the p-value, right? Determines how we calculate the p-value. Okay. For example, if I have my alternative hypothesis that mu1 is not equal to mu2, what that looks like graphically is I have area in both the tails here, right? So then my p-value would incorporate those two tails, right? Because for some stretch here, we're going to say, well, mu1 is basically mu2, right? They're not exactly the same, but they're not significantly different. So it's not until we see a difference that's significant, right? And how we determine that is by finding the area in the tails, right? So this would be our two-sided p-value is the area in both the tails. So I'll underline that in pink to show that that's how you would find the p-value. Whereas if our alternative was that mu1 is greater than mu2, well, how do you find that p-value? Well, depends on how you find the difference, but let's assume that it's on the upper end. Right, one of the tails versus the other option if mu1 is less than mu2, right? It totally depends on how you calculate the difference, but let's assume that you'd be on the lower end if the difference was mu1 minus mu2, which we can assume it is. Okay. So that's going to determine how we find our p-value. And so that stays the same, but now what we're going to do is we're going to move away from relying on these distributions. So here, I even went ahead and drew a normal distribution, sometimes an ugly one, and sometimes a little bit weird looking. But in general, these are normal distributions that I'm drawing, right? And so now we're going to be able to shake that, right? And say, okay, well, it's not necessarily a normal distribution. So what can I do, right? And it all relies on having computers. And so instead of relying on an established sampling distribution, that is the normal distribution that I drew above. The normal distribution I drew above. Okay. So instead of relying on, okay, well, it follows a normal distribution, what we can do is we can run a permutation test. Okay. And so we can run a permutation test. Okay. And so a permutation test is going to be, you collect your data, right? You collect your sample and you look at your metric. Okay. And so you see a difference in sales, maybe of $20, let's say, okay, between group 1 and group 2, or AB, if you prefer AB testing. But I'll do group 1 and group 2 just to match what we were generically using before, right? So I have some observed difference in the means. Okay. So what I'm going to do is I'm going to put everyone in my sample together and create a new population, so to speak. Okay. And so I kind of dump all my entire sample, right? Whether they were in group 1 or group 2, I dump them all in. And then what I do is I randomly select people or observations from that sample that kind of, I don't want to say pooled because that means something special in statistics, but they are kind of grouped together. So this kind of lump of sample. And so now what I do is I divvy them up, right? Maybe group 1 had, 1,000 people in it, and maybe group 2 had 800 people in it, right? And so then what I would do is I would randomly assign observations in groups of 1,000 and 800. Okay, so I basically reproduce that split, right? Notice how I'm keeping those sample sizes the same, right? 1,000 and 800. And so I'm randomly assigning 1,000 people to group 1 and randomly assigning the remaining 800 people because I only have a total of 1,800 to choose from. And it's without replacement. So that's why everyone gets divvied up. But so the remaining 800 are lumped into group 2. Okay. Then what I do is now I can use those two groups, and just like I did initially with my original metric that I measured, is I can find the difference between the mean of group 1 and the mean of group 2, right? And then I can record that. And then because we have computers, I can do that all over again. And I can do that, 1,000 times, 10,000 times. And it really takes no time at all to run that permutation. Okay. So now what I'm going to be able to do is I'm going to be able to look at, okay, well, in all these different permutations, right, of the sample, how many of those had observations, so differences that were as extreme or more extreme than what we saw, right? And so that links back to our p-value, right? So that's going to be our p-value equivalent, is saying, okay, well, I can count how many of those samples satisfied that criteria, how many samples in the random permutations, right, were more extreme than what we saw from our test, right, or from our experiment, I should say. Okay. And so one thing that we are going to, so I will outline the steps of the permutation tests, but what we're going to see is that the results are similar. Okay. Similar to when we relied on the sampling distribution. So the results of the permutation test are usually similar to the classic use of a sampling distribution, so are usually similar to results using a sampling distribution, using a predefined sampling distribution. So a t-test or an f-test or a chi-squared. Z test chi-squared. Okay. However, right, it doesn't matter if we have numeric data or binary data, the methods for the permutation tests are the same, because I'll still be able to count the proportion, or I'll be able to calculate the average, right? So it really doesn't matter. But also we can get rid of those assumptions that about normality that we rely on. Okay. So the results of the permutation tests are usually similar to results using a predefined sampling distribution, but the benefit is that we use the same method, for both numerical and binary data. Okay. And we don't need those assumptions about normality. And we do not need assumptions about the normality of the data. That's a big benefit. Okay. So the results are going to be very, very similar, but it's more flexible because we do the same thing for numeric data, for categorical data. And remember, any categorical data can be rewritten as binary data, right? And so that's why we say binary data, right? But what we mean is categorical data. And we also don't need to check assumptions for the normality of the data, right? For example, if we were testing proportions, right, comparing two proportions, there were many, many assumptions that we had to check, right? We had to check that the data was randomly selected. That still is an issue, right? But we assume it was. And we had to check that our sample sizes were less than 10% of the population. It's usually the case. We had to check that I had at least 10 successes and at least 10 failures in each of the groups, right? So all of those, we don't really need those anymore, right? We had to have those because we were using the sampling distribution and they only work for certain conditions, but now we don't need that anymore. And that's really cool, I think. So permutation test. Let me pull it up here because I want to. Where is it? Man, I should have, there. Okay, found it. Okay, so permutation tests are going to be a number of steps. Okay, and so you have your and maybe I'll call it your 0th steps to match the textbook because they just jump right into it. But you record your initial observation, right? So from your sample, you record your initial, from your sample, record the initial observation. Or maybe I'll say metric here. So So you record the initial difference in the proportions of clicks, or the difference in the mean amount of sales, right? So whatever it is that you're looking at, it doesn't really matter, right? And that's the beauty of it. But from your sample, you're going to record that initial metric. Then what you're going to do is you're going to combine all your samples. So your entire sample is now going to be one. Okay? So combine the results. I'll just copy it from here, from the different groups into a single data set. Okay. Then randomly assign those results into groups of the same size as the original groupings. Okay, so then randomly assign without replacement. With replacement, then we're talking about a bootstrap. So then the same observation could happen more than once in each sample. And in that way, we could generate kind of larger samples than we actually have. But in this case, we're going to do it without replacement. So randomly assign without replacement results into the same sized groups as the original sample. And then, and maybe I should say original samples. Okay, so you divvy it up, and then you record the results, right? So whatever you record, record the resulting metric. Record the resulting metric. Here, we're not going to get there quite yet, but you could do it for more than 2 groups, right? There's nothing stopping you from doing it to just to 3 groups, to 4 groups, right? And so that's kind of the beauty of it as well, is we can apply it to many groups, not just 2, but we're going to focus on 2 because that's what we've seen before. Okay, and so okay. So then you record that resulting metric, and then what you do is you do that, say 1,000 times over, or 10,000 times over with whatever computing power you have. You could probably do 1,000,000 times over. Seems like overkill, but you want to get a good idea of the distribution of the metric. Okay. And so we can't get away from the distribution, the sampling distribution, but now we're creating it every time. Okay, and so then repeat steps 1 through 3 r times over. Okay. To yield a permutation distribution of the metric. To yield a permutation distribution of the metric. Okay. So then what you can do is then how you use it right, is you can compare your original metric to the distribution of the theoretical metrics that could be generated just randomly, right? And so these repetitions, right, the permutation distribution is the null distribution, right? So if I just throw everyone in a group, right, and then I randomly assign them to groups of the same size, then that's assuming that there's no effect of the treatment, right? And so here, this is equivalent to the null hypothesized difference. Okay, so this is equivalent to H naught, right? In a way, not, not directly. So this is, maybe I shouldn't say equivalent because it's so final. So this is the same idea as H naught, right? If the initial metric that I saw was not due to the effect of the treatment, well, then I should be able to see that many times over, or I should see something many times over that's similar to that if I just lump everyone in and treat them all as if they're in the same group and then just randomly assign them, right? That's saying that the treatment had no effect. Okay. So then what we can do is we then compare our original metric, right, to the permutation distribution of the metric. We then compare our original metric to the permutation distribution of the metric. We can calculate, and I almost said easily, right? But it is easy at this point, right? We can calculate how many of those permutations were more extreme than our original metric. We can then calculate how many permutations were more extreme than the original metric. If there aren't that many that are more extreme than the original metric, or potentially none, then there is an effect, right? And so so that's going to be the equivalent of a p-value. In fact, it is a p-value, but it's based on that permutation distribution. And so remember, the p-value is the frequency that chance model. So that's the permutation distribution. Produces a result more extreme than the observed result, right? And so I've been calling it a metric, but it is just an observed result. Okay. So it's the frequency with which the chance model, and this is in general too, the chance model, so the null distribution model, if we're using a predefined sampling distribution, or in this case, the permutation distribution, so the chance model covers both of those areas, okay, produces a result more extreme than the observed result. more extreme than the observed results. So then if we have this p-value, then we're still going to compare it to some specified alpha level, right? So we can then compare the p-value to a pre-specified alpha level, to a pre-specified alpha level. That should have been part of things that you should do before you collect any data or before you conduct an experiment. So we need to establish what metric we're using, our hypothesis, and we should also establish an alpha level before we even get started, because otherwise it's tempting to do stuff like, oh, okay, well, I'm going to use a 5% confidence level or an alpha level because I wasn't going to reject it at the 1%, right? But if you should be rejecting it, if you should be using a 1% or a 0.01 alpha level, then you need to stick with that, right? You don't want to up it to 5% just because then you get a significant result, right? You have to establish it beforehand. Okay. And so one problem is if we wanted to do multiple tests, right? So not just one significance test, but if we wanted to compare multiple groups, right? Then I'm exposing myself to errors, right? Type 1 and type 2 errors every time that I conduct this test. Okay, and so maybe I should add here the alpha level should be established before conducting the experiment. Right, so you don't want to change it because of your p-value. You want to have it set and then compare your p-value to the alpha level. There's a subtle difference, right? And so that's important. There are two errors that we expose ourselves to. Right. And that's going to be type 1 and type 2 errors. Type 1 error is when you reject H0 when you shouldn't. Okay, maybe the difference that you saw, right, or that metric that you saw in your original sample, maybe it was just because of just a weird random assignment into the original groups, right? And so that would be reason to reject H0, right? But maybe if you shouldn't, then you made a type 1 error. So that's when you reject H0 when you shouldn't. Yeah. A type 2 error we're less concerned with, because usually the problem is you didn't have a sample size that was big enough to detect a difference. And so that's failing to reject H0 when it should be rejected. When it should be rejected. So this usually due to small sample sizes. Right, and so the only way you could fix it is to increase your sample size so that you can actually detect real differences. But I see I'm really out of time. And so I'll let you go, but if you have any questions, let me know, but I'll stop this recording and I'll see you on Thursday.